All right, so we were talking about the X-ray bursts, or sometimes called X-ray bursters. These are coming from, as I was mentioning before, neutron stars that are in a binary system. Matter accumulates in an accretion disk, which you can see right here. They're showing the accretion disk. Of course, this is the jets of material that doesn't have to do with the X-ray burster. This is just material that is coming off of the neutron star due to these very strong magnetic fields. These are jets of material, and these jets of material, by the way, can be traveling really fast. I mean, they can approach 20% the speed of light, which is pretty amazing. Anyhow, that's a different story. So as this matter accumulates, in an accretion disk, of course, the accretion disk basically rubs against itself due to friction, and we can actually detect some of that. But then, when there's enough of that matter that falls onto the surface of the neutron star, it will ignite. It's hydrogen, of course. That's mostly hydrogen from the companion star that is accumulating in this accretion disk. And then when that material falls onto the surface of this really tiny object, remember, you're talking about a very, very tiny object, maybe 10 kilometers in diameter or so, maybe 20 at the most, you get this burst of X-rays because all of a sudden hydrogen is turning into helium. All right, and so this bottom picture is just an example of that. It doesn't last for very long, but that's basically what you see. Let's see. Most pulsars have periods of anywhere from 0.03 to about 0.3. So they're rotating more than once every, so faster than once every second. And then in the 1980s, so this you're going back 40 years. We discovered what were called, so all pulsars since the 1960s till the early 1980s were of this range, anywhere from about 0.3 to 0.03 roughly was their period of rotation. But in the 1980s, we found what are called millipulsars. Right? Milli is 10 to the minus third. So these are things that are rotating around, in 1/1000th of a second. Okay, so and we had no idea why these things were rotating around as fast as they were observed to be doing. Of course, now we have explanations for this. Let's go. And here's another even bigger mystery. Okay, so we looked and we found, I think it was about 2/3 of the millipulsars that were discovered in globular clusters, which is a bigger mystery. Okay, so let's go into why that's a mystery. Globular clusters are ancient. They are, at least the youngest ones. They're at least about 10 billion years old. Remember, the universe itself, 13.8 billion years. Okay, so these things are very ancient objects, and there's no new star formation, none whatsoever. Any star formation that took place in these globular clusters, these ancient objects that surround the Milky Way galaxy, surround other galaxies, took place. The star formation would have taken place long, long ago. Right? So the members of globular clusters, the individual stars, are either dying or already dead stars. And so we observed these millipulsars, and why is it that we found them in globular clusters? What the heck was going on? We really didn't understand. And it turned out that there were also X-ray sources. These X-ray bursts in many of these millipulsars. And so what we did is we reasoned out, okay, this is what's going on. Oh, here, hold on. Actually, this is the next thing. Here, let's go back to this. So the thing that we realized is there has to be matter falling onto the neutron star for it to spin faster, right? So again, the normal formation of neutron stars, they're going to spin maybe at 0.03. That would be like the fastest. But we're seeing some that, these millipulsars would be spinning at a rate of 0.003. Okay, so how did that happen? And so the way that we explain it is maybe there is matter that is, just to get back, let me step back just a little bit. When something is rotating, to cause the rotation to change, right? So when we change the rotation, that's called torque. So if you apply a torque, you always have to apply a torque at a right angle to the rotation, right? So if let me get my mouse here. So if the neutron star is spinning this way and then matter falls onto it, like this from the accretion disk, if matter is falling onto it in an almost perpendicular manner, that's going to give the neutron star a boost, a torque. And torques can slow down rotation, or torques can speed up rotation. And so with these milli pulsars, we think that the accretion disk, where we had an accretion disk that's rotating around in the same direction as the neutron star, and then the matter falls on in just such a way, so it's almost perpendicular to the rotation axis, that it speeds up the rotation, right? Because how are you ever going to get millipulsars in a globular cluster, in something that's 10 billion years old? I mean, there's no new star formation, so there must be already existing stars. So what we've reasoned, of course, is that these are neutron stars in binary systems. The matter falls on into an accretion disk, and then the accretion disk will speed up, as it falls onto the neutron star, it will speed up the rotation rate. And by the way, this rotation rate, so you're talking about 1/1000th of a second for this thing to rotate around. Our theoretical calculations put that at the almost the limit at which as fast as these things can spin. All right, let me explain what I mean by that. If they spun even faster, right, than these millisecond rotation rates, if it spun even faster than that, they would just spin themselves apart. Like the neutron star just could not. There's what's called a centripetal force. It's not really a force, but it acts like it's a force. It's the same thing that happens, like, for example, if you're driving along and you make let's say a right turn, right? So you're driving down the road, you make a right turn, and you feel your body, pushed to the seemingly pushed towards the left, right? When you made let's say it was a really sharp right turn, you feel your body pulled towards the left, and that's called centripetal acceleration. It has to do with your body wants to continue moving in the same direction that it was moving. That's called inertia. And then the sudden change in direction, your body wants to keep going in the same, and so it seems like you're being pulled to the left. Anyhow, that's a property, that's a physics property that's well understood. When these things are rotating that fast, the material inside of it, even though it's really compact material, if it was rotating any faster than that, this outward force, or also known as centripetal force, would basically break the pulsar, the neutron star apart. It could not handle that, and just would dissolve. And that's not what happens with these milli pulsars. Okay. All right. I mean, and of course, if it did, we wouldn't see them as milli pulsars, right? So maybe some of them already have done that, but we don't have any evidence for that. Like, you always have to have evidence in science, in any of the sciences. And of course, if somebody could witness, if we could observe like a milli pulsar just ripping itself apart by accumulating too much matter and rotating too fast, that would be pretty revolutionary if somebody actually observed that. But nobody has, mind you, and not that anybody's. People are looking. There's always research in different areas. That is one of them. That's an ongoing area. All right, so here's something interesting that was observed in 1992. Now you have to go back. 1990, in the early 90s, we humans, that is, only knew of the 8 planets that existed around our sun. Okay, right around that time is the first time we were able to, using the Doppler shift, as a matter of fact, to determine that there were planets around other stars. I mean, we always thought that there were planets around other stars. There was no reason to think that our one star, in the Milky Way galaxy, which is populated by perhaps 200 billion other stars, there's like no way that we would be the only ones with planets. Our star would be the only ones with planets. And so right around the early 90s, we first were able to, it really had to do with computer technology advancing to the point where we could work out the details. Now, we still, for the most part, don't actually see planets around other stars. It's an indirect measurement that we make. And this was actually this was observed with radio telescopes, in a neutron star system, which seemed to have a planet. So what we did is, remember the pulses, right? So you got a pulsar, right? And by the way, let me back up just a little bit, just to emphasize something really, really important about this. All pulsars are neutron stars, okay? All of them. But not all neutron stars are pulsars. So now why is that, right? A neutron star, of course, is this rotating, this rotating object, and one of the reasons that it might not be a pulsar is the pulses might not be aimed. Just like if the lighthouse, is not aimed towards your direction, for some reason, you won't be able to see that lighthouse, right? So it's the same thing. If the neutron star is spinning in such a manner that is, essentially perpendicular to our line of sight, you're never going to see that pulsar. The other thing is, we think that the pulsar part of a neutron star's existence only lasts, maybe, I don't know, just several million years, up to maybe 100 million years, which again, in the age of the universe, which is 13.8 billion years, these neutron stars will have had time to stop pulsing. Or, it's not, they're not pulsing, but the pulsar effect, this lighthouse effect, will have reached a point where we can't see that anymore. All right, so let's see. So one of the things that was observed is the pulsar. These pulsars, or this one particular pulsar, which I think was in the southern hemisphere. Anyhow, the pulses